Swayam Prabha. Digital India. Educated India.
Welcome to this lecture. So, in this lecture we are going to finish off this droplet combustion related studies. So, one other phenomena that was interesting in the case of a droplet and one should mention is that if a droplet actually is composed of two components, basically many of the fuels are actually two component fuels, right. So, and these components can have a wide range of volatility, that means their saturation vapor pressure may be very different, right. Say for example, you have ethanol with some other fuel, say for example ethanol is a high vapor pressure fuel, other fuel like dodecane may be a very low vapor pressure fuel, right. So, once you operate with a mixture of two or more fuels, okay, there can be volatility disparity between the two fuels concerned, right. In those cases what happens is that, and this observation what comes from C.K. Law's work, is that you see that the droplet basically undergoes a shattering. This is not the kind of shattering that you see in the case of your droplet atomization studies. This is very different, right. You see a droplet burning, they actually let the droplet fall from a drop tower essentially, and they saw that this is the streak. This means the droplet is just burning nicely, okay. But at the end it kind of shatters and forms this all this nice, it is like almost like a Diwali firework, right. Why does this thing actually happen? Okay. So, this happens is because the multi component droplets exhibit something which is called diffusional entrapment. What does diffusional entrapment exactly means? Okay. So, once diffusional entrapment happens, the droplet is actually prone to this kind of catastrophic breakup which is called micro explosion. Okay. So, what is diffusional entrapment? Diffusional entrapment is very simple. When you actually have two component fuels, like for example you have a droplet over here, let me draw it properly. Let me go to the journal and then that may be useful. So, if you have a droplet like this over here and it is composed of two components. So, what happens is that after some time there is an accumulation. So, what happens is that the more volatile component actually escapes, right, more volatile component escapes. Okay. So, the surface very near to the droplet surface, okay, there is an increase in the concentration of the non-volatile component, is not that so, right. There is a increase in the concentration of the non-volatile component. But so what it does is that, but in the center of the droplet you still have a lot of volatile component now present, right. Okay. But because of the presence of this non-volatile component at the surface in increased amount, what it happens is that it leads to an increase in the surface temperature, right, because the volatility is low. So, the surface temperature goes up. As the surface temperature goes up, okay, this volatile components which are trapped in the interior of the droplet, their temperature also goes up. If the surface temperature goes up, the Tc should also grow up, right. Okay. Because of that, as this surface temperature goes up, this might exceed the boiling point of the volatile component, which is basically shown over here. Okay. So, the droplet temperature attains a higher value because it is controlled by the more abundant, higher boiling point low volatile component. The droplet temperature is heated beyond the local boiling point and provides a substantial amount of superheat. That means the center which still contains that volatile component now is raised above its boiling point, right. If that is sufficiently high, then the liquid will homogeneously nucleate. This is homogeneous nucleation, this is not heterogeneous nucleation, which you will see what boiling is and what nucleation are. So, homogeneous nucleation essentially means that it does not require a surface, it happens at the molecular level, right. So, you can homogeneously nucleate and gasify, leading to, so it forms those bubbles, it starts to form those bubbles inside the droplet. So, you now have these small bubbles within the droplet, right, and these bubbles grow, they create a pressure surge and causes this catastrophic breakup. So, it is almost like bubbling inside a droplet, right, which grows and shatters the whole droplet, right, because of the pressure expansion, right. So, what happens over here is very simple, you need a non-volatile, you need a very high degree of volatility difference. When there is a high degree of volatility difference, the more volatile component starts to preferentially evaporate at the surface, leaving the less volatile component on the surface, right. As a result of that, there is a temperature surge on the surface, right. As there is a temperature surge on the surface, the high volatile component which is now trapped in the droplet core also experiences a temperature surge. And if this temperature surge crosses the boiling point and the superheat limit, okay, some of these, this high volatile component within the droplet core may actually form bubbles, and these bubbles will grow, leading to intense internal pressure buildup and lead to catastrophic fragmentation, right. So, homogeneous nucleation will initiate at a location where the temperature exceeds the local concentration weighted superheat, right. When the superheat limit is exceeded, this is what happens. It has been found in many cases that the limits of the superheat is about 90% of their critical temperature. So, this value can be really high, right. It is just not the boiling point, it is very close to the critical point sometimes. For example, the critical point for water is quite high, okay. So, it can be like that as well, okay, but this is the mechanism, this is called what we call diffusional entrapment. This does not require a surface, this is normal, the process is very normal, okay. So, micro explosion happens, so there has to be an optimum differences. The low volatility component will drive up the temperature, the high volatility component will lead to internal nucleation. So, both the components has got their own role to play, okay. So, the droplet center has got the highest concentration of the volatile components, while the droplet surface has the highest temperature. So, homogeneous nucleation occurs somewhere in between these two locations. Micro explosion can, this leads to micro explosions, what we already said, okay. It also can improve the utilization, because through micro explosion you generate these very small dotted droplets, right, which actually is like a secondary source of atomization, so to say, right. So, even when the droplet is burning, see, we talked about atomization which was purely driven by aerodynamics, or it was driven by other things, right, not by heat per se. Here it is driven by heat. So, basically through these bubbles and boiling and other things, we are able to get this this micro explosion things to happen, got it. So, it may improve the secondary atomization behavior, and so, but for this to happen you need a lot of difference in the volatility, okay. So, one other thing, in the case of a phenomenology of a droplet combustion or a spray combustion is that, okay. So, what we have considered so far is how a droplet burns, how the droplet explodes, okay, what are the differences in the burning modes, etc., etc. Now, one may be really concerned about that how we can actually say, do the droplet really burn, right, because you have a flame if you look at it. So, what we are saying is that there is a flame that surrounds the droplet, right, like that. Of course, this can be a little egg shaped also depending on the flow and other situations. Does it happen like that, or does the droplet completely vaporize before it actually, before the flame is actually initiated, got it. So, if you look at this particular diagram, what happens is that there is a droplet which approaches a premixed burning zone, and this is basically the droplet flame that is actually burning, and then ultimately it becomes gas. So, far upstream what we have fuel droplets, fuel vapor and oxidizer and inert gases like here. As it approaches, the droplet size slowly becomes smaller because it evaporates because of the heat that is released, okay, and after that the droplet starts to burn. Now, if the characteristic time for penetration of the droplet through this preheat zone, if we consider this as the preheat zone, that is given by this particular parameter. This is basically called the flame speed. Okay. We let us not consider, let us not dwell a lot on the flame speed. Okay. Flame speed, you can read up your Stephen Turns or other types of books to find out what flame speed is, right. Then there is also something called the droplet vaporization time, which we already know, it is R square by kV. kV was the burning rate of the droplet, right. Okay. Now, if we compare these two numbers, if these two time scales are the same, that means the droplet vaporization time and the droplet traversing time, if they are both the same, that means the droplet turns into vapors by the time it crosses the preheat zone, right. So, a droplet takes say x seconds to pass a preheat zone, right. The droplet vaporization time, which is the time that is required to completely vaporize the droplet, is also x seconds, right, or lower than that. What will happen? The droplet will actually completely evaporate, correct. Okay, before it actually gets into the preheat zone. Now, that is an important consideration over here, that this is what happens when the droplet. So, when these two ratios are the same, okay, we get a minimum droplet diameter, okay, below which the droplet burning does not happen at all. The droplet completely evaporates in crossing the preheat zone of the flame. Got it? The droplet completely evaporates in the preheat zone. So, there is nothing called droplet flame, and that is something like 10 micron for atmospheric stoichiometric alkane air flames. Got it? So, any droplet which is below this basically evaporates completely before it actually burns. Got it? Got it? So, so that is the one of the phenomenology. Okay. One other thing that we are going to consider as a part of this lecture is basically what is called the dense spray combustion. As we said, we have considered single droplet combustion, we have considered single component, multi component droplet, we have looked into micro explosion, but as we know, in most of the sprays the droplets comes in clusters, right. There are many droplets, too many, right. So, the droplets are very close to each other, and in some cases the spray interior can become sufficiently oxidizer lean. So, spray flame actually burns either as a single flame which surrounds clusters of droplets, right. In that case, what we call it's a group combustion or a cloud combustion. So, you cannot isolate these nice little flames. Okay. So, most of the Chew and co-workers have proposed the use of something called a group combustion number, which is called G, which is basically given by n into this particular quantity, where n is basically the total number of droplets. Okay. And so, large G essentially means that there are a lot of droplets, right, and large G actually favors group combustion, whereas single droplet combustion is favored for small g. So, it is basically a geometric definition, that the definition of G, and so it does not include the effects like of droplet vaporization and heat transfer to the droplet cloud, etc., etc. It is just a number that we are proposing to isolate that what are the different combustion modes that are available for a spherical droplet cloud. So, this is an important figure. So, if you look at this very carefully, what you will find is that this is for very high G, the first one, very high value of G. Okay. You can see clearly three regions. Okay. There is an external flame. So, there is a single flame, right, which surrounds this droplet cloud. Okay. There is an evaporating core. Okay. This is an evaporating droplet layer or an evaporating layer. What do you mean by evaporating layer? That there is a cloud of droplet that actually evaporates. Center, there is no evaporation, no evap, as you can see over there. That means the center of the droplet does not even see, right, the flame, it does not experience anything. Okay. So, what happens is the inner core of the droplet cloud is fully saturated, vaporization takes place only within a thin layer, and the vaporized fuel diffuses outward and reacts with the inward moving oxidizer and forms this cloud diffusion flame. Got it? Okay. Now, if we move to a slightly lower G, that means you are continuously reducing this G, what happens is that the core now starts to participate in the evaporation. Now, it is a vaporizing core, the entire core vaporizes, right. The flame is still a common flame for everybody, right. It is not distinct, you cannot distinguish that which droplet is contributing to the flame, right. This vaporizing layer now has become very thick and it encompasses all the droplets in the cloud. So, all the droplets are actually evaporating, they are interacting and evaporating, right. And but the flame is established outside this droplet cloud. Now, if you reduce the G even further, that is the third mode, okay, what you will have is that you will have a main flame like this and you will have this individual droplet flames. So, this is fascinating, right. So, you have a flame of individual droplets, you have a main flame which is a common flame, and then there is a vaporizing core, all right. Okay. So, the diffusion flame has moved inward now, it was here, right, it has moved inward inside this droplet cloud, right. Some of the droplets are actually burning as individual pieces, okay, and but the majority of the droplet are burning as a whole in this diffusion cloud, right. Okay. So, individual droplet combustion is happening outside this main flame, right. Further, for very small values of G, you get actually individual flames, there is no main flame, all the droplets are burning as individual pieces, right. So, these are the 4 modes of combustion, right. You are clear about this. So, these are the 4 modes of combustion that you see over here. Okay. One is there is a non-vaporizing core, there is an outer vaporizing layer, then there is the flame. In the next case, you have a vaporizing core and an outer flame, then you have a main flame, a vaporizing core and individual droplets which are burning outside the main flame, and then you have a case of individual droplets which are burning as flames. Got it? Okay. There are, in the case of jet flame, you have a little bit more suggestive things. For example, there is an external group combustion behavior, as you can see. So, this is the group combustion. Okay. So, there are multiple flames present. So, this is, for example, the individual droplet cloud. So, there can be pockets of such clouds, and remember there is a flow droplet interactions also in these cases, right. So, there is now there is internal group combustion over here, okay, and this is basically the potential core, okay, where the droplets do not feel anything. Okay. So, in a flame like this, okay, you can have this kind of non-homogeneous distribution of droplets and non-homogeneous distribution of the flame front. So, there may not be one single flame, there can be multiple flames, right. There can be individual droplets burning, there can be external sheath combustion, there can be internal sheath combustion also, right. So, and there can be a lot of variation of G. So, it is not just a one value of G, the G varies in a spatial manner, okay, in this particular case. So, this is a very famous diagram which was proposed by Chu and co-workers, right, where they actually said for the total number of droplets divided by the plotted against S. Okay. So, this is the group combustion behavior or a regime map, so to say. So, in this regime maps, what you have? You have this internal group combustion lying here, single droplet combustion lying there, right. Okay. And then external group combustion here, external sheath combustion here. You can see what each of those symbols means by these small cartoons, okay, over here. There are transition bands also. So, so it involves, as you know, that the spray involves a lot of droplets. The simplest analysis is to estimate the combustion rate as a sum of the individual combustion behaviors, but it is not the case, as we already saw that interactions can change the gasification, it can change the ignition, it can change a whole lot of things, right. So, interaction of the droplets within that environment are given by these collective interactions or what we call the group effects. And this is still a hot field of research, because nothing is concretely known how to model these kind of systems, how to know the dynamics of these kind of systems, right. When you actually have, say, a flame that is established in a gas turbine, say for example, where it has got strong swirl, strong turbulence, multiple ranges of droplets, okay, it is very difficult to isolate and know about each of the flame, right, and what kind of a flame is established in what kind of a range. That is still a pending question that we have. In addition, there are other types of things, say for example, as we know already that droplet inhomogenization happens almost because of the flow conditions, okay, and that is given by something like a Stokes number, right. If you do not know Stokes number, then you just read it up, okay. So, it essentially means that smaller droplets are actually entrained better, okay, and these droplets forms these homogeneous clusters. Multiple such clusters can be formed inside a flow situation, as you can see from this little cartoon over here, okay. So, when you try to ignite a flame like this, okay, it burns at different ways, the different group combustion behavior at different spatial locations essentially, right, okay. So, unlike gas diffusion or the gas phase combustion, right, this is a very complicated beast, so to say, because of this multitude of droplet sizes and multitude of flame group combustion, compound cluster combustion, that is what we call it. It is not a simple cluster anymore, it is a compound cluster that you actually see over here, okay. So, these are the kind of things that one should know, okay, once one tries to look at the combustion behavior of droplets as such, okay. So, this part is still a subject of very active research, okay, and people have not been able to come to a very concrete, you know, theoretical framework for this. There has been a lot of these things that has been kind of attempted, okay, in a lot of studies like this, okay. So, this part I want you to just know that there are 4 such stages. This is the most important thing, right, depending on something called a group combustion number, okay. And we have covered the almost the entirety of your droplet combustion. We have skipped a few like miscible mixtures, okay, multi component droplet combustion and ignition and extinction of sprays, okay. So, that you can read up if you want in your spare time. So, these are given as like kind of reading materials. We also know how the droplets interact with each other, right, and when the interaction approaches the single droplet burning regime. We also know what external convection does to the burning behavior. We also know about the the variable properties part we also skipped, but you can read this up, okay. It is not going to be difficult, you just read it up and see that what you understand out of it is given as a reading material. Then internal recirculation, droplet with internal recirculation is also covered in kind of very details in this particular section, and we say that Hill spherical vortex is once again used, okay, for this setup. Then we talked about fuel accumulation, how the fuel actually accumulates, because normally the d square law assumes that the consumption and the evaporation of fuels are the same, okay. We also said that the droplet heating time, active heating time is only about 10% of the total lifetime of the droplet, okay, and we also showed the 2 limits of droplet vaporization when you actually have a flame surrounding it, okay. And lastly, we also said we discussed in depth about the single component droplet combustion behavior and the d square law that we already did in the let us go to the journal, and the d square law that we did over here. We also explained what is called diffusional, this is diffusional entrapment. So, this you should know the degree of superheat that is required, okay, and we also covered a lot on the spatially uniform but temperature varying profile, the concept of Peckley number over there, and lastly we also did the d square, this is the d square law, okay, and we showed that the gas phase quasi steadiness is also holds over here. Remember of course that the flame temperature is the adiabatic flame temperature for the stoichiometric ratio that is given, okay, and the reaction standoff distance ratio remains constant. Okay. So, with this what we do is that we are going to finish this droplet combustion related studies, okay, and what we are going to do in the course of the next couple of lectures that we have left is we are going to look into another important aspect of multiphase flow, which is basically the bubbles, or in other words it is called boiling, right. So, let us introduce in the next 2 minutes about what boiling is, okay, and before we move on and explain it in more details, all right. So, boiling is not evaporation. If you look at this particular little slide over here, boiling is not evaporation. Okay. Once again we are going back to Amir Fakhri and Yuan Zhang's book. Okay. So, boiling requires much larger temperature between the bulk liquid and the heating surface than evaporation, right. So, you can have evaporation and you can have boiling, as you can literally see evaporation curve is this. So, the difference in temperature between the wall and the liquid is very low, right, where in the case of boiling, okay, there is a much larger temperature difference that exists, okay, and evaporation is a surface phenomena, boiling is not a surface phenomena anymore. The thermal boundary layer that you actually have in the case of evaporation, okay, is not very precise in boiling because of the large scale motions, okay, that are created within the liquid, the churning that are created within the liquid. So, we will there are different types of boiling and there are different types of other things which we are going to do in the following lecture, where we are going to see that boiling is bubbles, essentially the story of bubbles, like we had the story of droplets, it is the story of bubbles. This boiling can be of different types, homogeneous, heterogeneous, nucleate, there are different whole classes of boiling, okay. And not only that, boiling and evaporations are very different. Evaporation is a slow process, boiling is not a slow process anymore, right. So, we just briefly saw how boiling can enter into the picture in that micro explosion of droplets. Here we are going to formally give you an idea, we are not going to go into too much depth because of the lack of time. We are going to just emphasize that what boiling is, what are the different types of boiling, some equations which represents the boiling, okay. But these are the two main differences. Evaporation requires a much lower temperature difference. In fact, any small temperature difference can drive evaporation. If you leave a saucer of water out in the open, it actually evaporates out, right, okay, but it does not boil obviously. So, boiling requires a much larger temperature difference and the thermal boundary layer is very imprecise in the case of boiling. So, we will see in the next lecture that how we can actually analyze this boiling in more details. Thank you.